So I want to welcome you to factor analysis. Before factor analysis, I think I walk you through what I call a principal component analysis. So now you know what principal component analysis does. You know what it can be used for. You know the essence of applying principal component analysis. You know the mathematical procedure or statistical procedure to be able to generate principal component analysis. I walked you through that the other time. And principal component analysis will also be mentioned in factor analysis because the factor analysis is, it's also dimensionality reduction technique, just like principal component analysis, only that the factor analysis actually go further, by trying to trace factors attributed to the input variables. We didn't do that in principal component analysis. A quick reminder of what we did in principal component analysis. What we did in principal component analysis was that we got some set of variables that are correlated and we're trying to convert them into uncorrelated ones. That's number one. And the number two things that why we do principal component analysis is to reduce the dimensionality of the multivariate data set. What do I mean? What do I mean by reducing the dimensionality? Because in a situation where you got a lot of input variables, you actually need to reduce the dimension because of the fact that, if we want to analyze, we need simplicity. Okay, situations is actually going to be complex around, over dimensional nature of a data set. Okay, and that is the reason why we need simplicity. We actually need to reduce. Of course, that actually came with price, and the price is that we actually traded little accuracy. But you know what? The principal component analysis is a technique, though there's going to be what I call information loss, but it's going to do that in a way that the majority of the information will still be preserved. And I could remember when I constructed the principal component, we have the first principal component, we have the largest variation, so that you don't need to use all the principal components. Okay, so you can use few of the principal components that actually explain the largest percentage of variance. So that was what we did under the principal components. So I try to review the principal components so that you'll be able to know the difference between the principal component and what we want to do right now. So for factor analysis, I want you to look at the word factor. Okay, it means the input variables that we are working with actually have one or two factors that are hidden, okay, that we call latent, that are not observed, okay, and we're trying to unravel them, okay, believing that the input variables that we have, they're actually going to have like a common factor or a specific factor, okay. So you're actually going to see that as I'm going to be walking you through, through that, okay. So this is factor analysis. In the outline today, you're going to have an overview. We're going to have the basic concept. We're going to have a factor analysis model, I'm actually going to walk you through statistics associated with a factor analysis. When I say statistics associated with a factor analysis, I'm actually referring to, statistical tests, okay, that we're actually going to use when we are discussing on factor analysis. Can you guys hear me?
Yes.
Okay. Thanks for confirming that. Okay, so another thing that we're going to talk about is, one of the objectives, the outline is conducting factor analysis. And if I want to conduct factor analysis, of course, we have algorithm, we got a procedure that we're actually going to follow systematically. Number one, we're always going to have what we call a problem formulation. Number two, we need a construction of the correlation matrix. And somebody will be wondering, why do I need correlation matrix? Why not variance covariance matrix? Let me confirm to you, correlation matrix, more than 90% of researchers throughout the world prefer to use a correlation matrix, in factor analysis. I'm going to say that again. More than 90% of researchers in the world prefer to use correlation matrix, a factor analysis, why less than 10% prefer to use variance covariance matrix in factor analysis. Because with the correlation matrix, you have been able to scale, you've been able to standardize the data. Because we actually need standardization. I told you the other time, the essence of standardization, because when I have one or more than, one or more input variable, they actually each of them, they are actually going to be measured in different units. When they are measured in different units, some of them are likely to have a wider range than the other one, and we don't want the one with a wider range to actually dominate. And that is the reason why we need to standardize. And the correlation matrix is actually a standard, with a correlation matrix, you've been able to scale the data. Though we use covariance matrix as well, but the covariance matrix is more or less the deviations of, the deviations of the input variable around their respective means. But I want to tell you, in factor analysis, more than 90% of researchers prefer to use correlation matrix, while less than 10% of researchers use covariance matrix. Okay. Now, the next thing we're going to talk about is the method of factor analysis. We're going to talk about the number of factors. How do we decide on the number of factors? We're going to talk about what we call rotation factors or rotation of factors. Then how do we interpret our factors? Then what about factor scores? Then the model fit. We're actually going to, looking at a factor model, just like the way we normally test, the way we normally subject models to diagnostic testing, we're also going to subject factor model to diagnostic testing, okay? We're actually going to evaluate the model to be able to see whether the model is adequate, okay, in terms of the factors considered. So these are, the outline. These are what I'm actually what we're going to be doing in factor analysis. Okay, so I want to introduce you. So when I say factor analysis, let me quickly remind you of this. You remember in your high school, when you are given an expression, maybe it could be a quadratic expression, it could be a cubic expression, it could be an expression of polynomial of degree 4, degree 5, and so on like that, and they ask you to factorize. So what is the essence of why are we factorizing? And what is the meaning of factorizing? You know, when you are factorizing, it's just like we got something complicated and we actually want to filter it out. It's more or less like breaking, splitting. Okay? And let me tell you, and that is the reason why we said, okay, it's a class of procedure used for data reduction and summarization. The data set that we collect from the field of inquiry are massive in nature. At times you collect, across thousands of individuals, and you measure a lot of variables, like 5,000 variables. Look at the dimension of that. It's going to be huge. And you know what? If we want to analyze data set, we actually need to put it we need to put them in order. They need to be put in a simplified form before they can be successful, efficiently analyzed. And that is the reason why we are actually looking for a way to reduce and summarize our data. But we know that when we do that, there's going to be a loss of information, but the majority of the information will still be preserved. Okay? So factor analysis, just like principal component analysis, factor analysis is another dimensionality reduction technique. Okay? It's another dimensionality reduction technique. Now, it is an interdependence technique. What do I mean by interdependence technique? Interdependence, you remember when I started this course, I was talking about some variables are interdependent, some variables are, they depend. So what we mean by that, there is no clear distinction between the response and what we call the input variables. Okay? We cannot really say if one is dependent. We cannot really say if one, so if I have set of variables like that, where it is kind of difficult to tell which one is the response, okay, then the factor analysis can actually be used, to figure things out. Now, factor analysis is, used, perform this role. It can be used to, to identify underlying dimensions or factors that explain correlation among set of variables. Now, let me tell you this. We got variables that we actually want to talk about. But you know what? We believe we're in a world where things don't just happen, but something make something to happen. I'm going to say that again. Things don't just happen. Something, we believe a particular factor or factors actually contribute to the occurrence of that. And that is the reason why in factor analysis, we actually want to identify underlying dimension. There's an underlying dimension of factors, that explain the correlation among set of variables. Because the input variables may be correlated, but they don't just correlate. There's a latent variable. There's something that is hidden. There's a factor hidden that we don't see right now that actually make them to correlate in the first place. You remember in principal component analysis that when we have a problem in multiple linear regression, okay, when we have a problem of multicollinearity, what do I mean by multicollinearity problem? You know, when the predictor variables are correlating, you know, we use principal component. I told you before, I walk you through that, how we can use the principal component analysis to be able to convert the correlated set of variables into uncorrelated ones. But you know what? The principal component analysis cannot do the job of identify underlying factors that enable variables to correlate among themselves. That is what factor analysis does. The factor analysis will enable us to trace the hidden factors, the latent variables, you know, that actually cause these variables, the input variables, to be correlating. I told you the other time that things don't just happen. There's always something that causes things to happen. We're in a world of cause and effect. We're in a world of cause and effect. There's always, you know, there's always going to be causation. Something caused something to happen. In factor analysis, we actually want to identify some factors that actually cause correlation among the set of input variables. And that's exactly what this is actually talking about. To identify underlying dimensions of factors that explain the correlations among a set of variables. Okay, so the second function of factor analysis is to be able to identify a new, smaller set of uncorrelated variables so that I can replace the original set of correlated variables. We know the penalty that's actually going to be incurred when we use the correlated variables. It's things, you know, it's actually not going to work so fine. It's not going to work well. So we actually need to have a new set of variables in place that have already been trimmed. Okay, so, and that is one of the, you know, function that the factor analysis actually share with the principal component analysis. But let me tell you something. In factor analysis, we also make use of the principal component analysis to perform a function as well. As time goes on, I'm going to walk you through how, you know, as one of the steps at times in factor analysis, we can also use the principal component analysis to figure out stuff. I'm going to tell you as time goes on. Okay, I want to start with this. I want to take my example from psychology. What I have right here, actually want to determine factors underlying selected, you know, psychographic and lifestyles. Okay. If you take a look at what I have right here, you're going to see whether going to a party, whether to play baseball or watch movies and stuff like that. You know, let me tell you something. If I decide to go to movie, or I decide to go to baseball, or I decide to, you know, go to party, or I decide to play, or I decide to choose whatever lifestyle I choose, you know, whatever lifetime I choose, I believe is actually you know, cause can be attributed to a certain factor. There's a reason why I got to choose a particular lifestyle. Okay, there's a reason for choosing a particular lifestyle. Why do I have to choose baseball over movie? Why do I actually choose movie? You know, stuff like that. At times, a lot of things may be occupying our minds. Okay, so now in the analysis of factors, we actually need model. I told you the other time, we are in a world where we actually, as human beings, we want to capture the world, we want to control the world. Every happenings in the world, we want to put them under control, so that will enable us, you know. And if we want to put the world under control, if we want to understand the world, then it means we're actually going to do that by modeling. Okay, we got to do that by trying to model. So if we really want to identify factors that are that are attributed to a particular input variable, then I actually need to use a model, so that that model will look like what I have right here. Okay, if you look at what I have in this model, this is like a particular input variable. XSI is a particular input variable that we actually believe, you know, can actually be explained by one or more factors. So if you take a look at what I have right here, this is a model that I'm talking about. So what I'm trying to tell you right now is that a particular input variable, okay, can be written, okay, in terms of the fact or combination of factors, and that's exactly what we have right here. Okay, it's actually going to be a linear combination. Okay, so if you take a look at what I have, you're actually going to see that, and that was why I said each variable is expressed as a linear combination of factors. So the F1, F2, up to Fm, this is like having M number of factors, you know, that actually explain a particular input variable. Okay, and we get another component. Okay, if you take a look at this component, I said the factors are some, you know, the factors are some common factors. Okay, common factors plus a unique factor. Okay, common factors and plus a, you know, you got a unique factor. Okay, so if you take a look at this is acting like a systematic part of the model. Can you see that now? Like a systematic part of the model. And if you take a look at this is like the one that is common to all of that. Okay, this is like having a specific factor, and this is like having a common factor. Okay, so what I'm showing you right now is what we call a factor model. Okay, where the xi is the I standardized variable, and the aij is the standardized, multi-rare coefficient of variable I on common factor j. Okay, and fj will be common factor j. Okay, so that is going to be the fj. When I say the fj, okay, it could be f1 or f2 or something like that. Okay, and we got a vi right here, which is a standardized, rare coefficient, like regression coefficient of variable, or of variable I on unique factor I. Okay, and while ui is a unique factor for variable I, and m is actually the number of factors that we have. So what I'm showcasing right now is what we call a factor analysis model. And every factor analysis model will enable you to express the input variable as a functions of factors. Okay, uh, the first set of weights, which I call the factor score coefficients. if you take a look at the model, okay, if you take a look at the model, you're actually going to see that these are factors. Factors are like, if you look at this model, factors are like predictors, right? And then they are like predicting the input variable, okay, a particular input variable. Then each factor actually have a weight, okay. These are the weights of each factor, okay. Just like what we did, in linear regression, where we got, regression parameters, okay, that will actually tell us the contribution of a particular a predictor, okay. So we also have that in factor analysis, and that was why we said the first set of weights, the factor score coefficient, we call them factor score coefficient, just like the way we got regression coefficient, okay? So are choosing so that the first factor explain the largest portion of the total variance. Let me tell you this. In the principal component analysis, the first principal component analysis explain the largest variance. Let me tell you this. If I have 10 variables, I'm actually going to have 10 principal components, okay? The variance of the first principal component is believed to be, the highest, okay? Also, in factor analysis, the first set of weights will be chosen so that the first factor will explain the largest portion of the total variance. If you take a look at what I have right here, this is the first factor, this is the second factor, and so on like that. But the way the model is actually going to be chosen, the first factor right here, we got the largest variance. That's exactly what I'm trying to talk about, okay? So first factor explains the largest portion of the total variance, okay? Then a second set of weights can be selected, okay? So that the second factor explains most of the residual variance, subject to being uncorrelated with the first factor, okay? So like I said, these are principles, okay, so that we apply in factor analysis, okay? So this same principle apply for selecting additional weight for additional factors. Of course, in a linear regression model, some of you have heard about, adding more predictors into a model. If I want to add more predictor into a model, I have to justify the essence of adding predictors into a model. We got a lot of criteria that can be used, okay? I don't know whether you guys have heard about stepwise regression. Has any one of you heard about stepwise regression?
Yes.
Okay, so we also do the same in factor analysis, where we are trying to see whether, selecting additional weight, for additional factors, okay? So we also do something of that nature. Now, let me tell you this. If you look at I want to show you a model right now, and look at the one I showed you before. The one I showed you before is just relating a particular input variable with relating that to one or more factors. But do you know that a particular factor as well can also be expressed, as a function of all the input variables? Take a look at that. This is a particular factor, okay? This is a particular factor, okay? A particular factor can actually be written as a linear combination of the input variables. You remember, this is synonymous with what we did in principal components. If you look at principal components, at the end of the day, the principal component is a linear combination of, the input variables. We also have that in factor analysis, where a particular factor, but this time around is going to be a common factor, okay? That would be a common factor, okay? That means a common factor for the input variables that we're actually talking about. And that was why I said the common factors themselves can be expressed as a linear combination of the observed variables. Can you see what I have right here now? So where the Fi is going to be the estimate of the height factor, you know, a particular factor, and the W high, we actually see the weight or a factor score coefficient. I'm going to say that again. The weight or a factor score coefficient, and K would be the number of variables that we're talking about. Okay? And weight would be the number of variables that we are actually talking about. Okay? Now, the next thing I want to discuss with you, because I'm actually going to stop in 5 minutes, like I said, today is just going to be an introduction because you guys have a test tomorrow. You get a midtime tomorrow that is going to start tomorrow. And I really wanted to spend a lot of time, preparing for that. And that is the reason why I'm actually going to have a cameo appearance today. So I'm going to stop on this slide today. I'm going to explain statistics associated with factor analysis. Of course, if we have a factor model, we actually need statistical procedure, because we need to estimate parameters. So right here, we're going to estimate the weight, which I call the factor score coefficient. And if we really want to do that, of course, we have to go statistical. And that is the reason why I want to discuss something with you right now, that, statistics associated with the factor analysis. Number one, I will talk about Bartlett test of sphericity. Bartlett test of sphericity. Now, what do we use the Bartlett test of sphericity to do in factor analysis? We use this as a test. There's something that we call test of sphericity. And we actually use that to test the correlation matrix to see whether correlation matrix is an identity or not. Let me tell you something. What is the meaning when you have a correlation matrix? The diagonal element, can somebody remind me? Can somebody remind me right now? What can you tell me the numbers that we have in the diagonal of a correlation matrix? Can somebody tell me right now? Can somebody tell me the numbers that we have in the diagonal of a correlation matrix? What are these numbers?
They're all 1.
They are all 1. Good job. Those of you that, somebody said they are all 1. I think I had the voice of 2 people right now. The 2 people that I have their voice should send a message to me for extra credits. Good job. They are all 1. The meaning of 1 is a correlation between X1 and X1. Of course, the correlation between myself and myself is actually going to be 1 because I'm actually going to be perfectly correlating with myself. Because it's the same person. That's why you're going to have 1, 1, 1. And off diagonal of the correlation matrix, it's actually going to be 0. When you talk about identity, okay? So it is not all correlation matrices that are identity. So if a correlation matrix is an identity matrix, then what you are trying to say is that half diagonal correlation between any pair of variable is 0. That's what we're trying to say. Then in that situation, you're going to conclude that they are uncorrelated. Okay? Because they are input variables. We actually want them not to be correlated. That's what we want. We don't want them to be correlated. And that is the reason why we use Bartlett test to be able to test, is a test on correlation matrix to be able to see whether the correlation matrix that we have is more or less an identity matrix. It may not be automatically be it may not be exactly like an identity matrix, but what we are trying to do is to be able to test whether there's a significant difference between the correlation matrix that we have and the identity matrix. And that is the reason why I said it is used to test the hypothesis that variables are uncorrelated in the population. And the example is that the population correlation matrix is an identity matrix. That is what we want. So which means this particular test, since we're going to be working with a correlation matrix in factor analysis, don't forget that I told you before that, more than 90% of researchers in the world that work on factor analysis prefer using correlation matrix. And that is the reason why the Bartlett test of sphericity will actually be based on correlation matrix. Okay? So, and that test actually tests whether correlation matrix is an identity matrix or not. Because the moment it's an identity matrix, there is no problem anymore. There is nothing to factor. But if it is not an identity matrix, then then the applying factor analysis is actually, so I think you understand what I mean. Now, what I'm trying to tell you now is that the Bartlett test of sphericity will tell us whether we are working with a correlation matrix or not. Okay? Whether we are working with a correlation matrix, whether we are working with an identity, whether the correlation matrix is an identity matrix or not. Okay? Because we need information about that. Okay? And the implication is that if the population correlation matrix and identity, the implication is that pairs of variables are not correlated. But the moment it is not an identity, then we are trying to say the set of variables are correlated. Okay, so the Bartlett test will enable us to figure that out. Now, talking about the correlation matrix. Okay, the correlation matrix here is a lower triangle matrix showing a simple correlation. Okay, when I say lower triangle matrix, you're going to see that at times in a correlation matrix, okay, maybe correlation matrix of 5 by 5, the correlation between x1 and x2 is the same as the correlation between x2 and x1. Okay, we can actually focus on the lower triangular matrix. Okay, so between all possible pairs of variables included in the analysis, okay, and the diagonal elements are all 1. Okay, the diagonal elements, are all 1. I'm actually going to stop here today, and I'm going to continue from here next time, because like I said, I'm going to have a cameo appearance today. So is there anyone who want to ask question based on what we have done today? Is there anyone?